Hey there, geographers. It's Angela. So, this is going to be a lecture on earthquakes. Now, I don't know about you, but sometimes when I'm out and about driving, I could be flying or taking a walk. Maybe sometimes I'm stuck in traffic. I see rock formations. Maybe they might not look like this, but there are rock formations very, very close to where we live that do look like this. And sometimes, have you ever noticed that sometimes underneath the bushes, you can see certain colors of rocks, different colors of layers of rocks? And I don't know about you, but I'm become very, very curious. So what do you see and what do you wonder? Have you ever wondered about life in the West Coast, life in Southern California, and how you can be at sea level and all of a sudden turn around and see mountains that are over 8,000 feet high? Or, say, for example, if you've ever gone to Northern California or Oregon, and in Oregon, you see the same thing. You turn around and you look at Mount Hood and you just think to yourself, wow, it's amazing. How did those things ever happen? And that is a real sense of curiosity. Now, if you've never wondered any of those things, it's fine. We're going to go over why we have mountains in Southern California, we've already gone over why we have volcanoes in Oregon because of the Cascadia. We have tectonic plates in a subduction zone, oceanic plate going and diving underneath a continental plate. And the result of that plate movement means that we are going to experience earthquakes. And the humans that are living near these plate boundaries are going to experience more earthquakes than the people who live away from these plate boundaries. So, we've already talked about plate tectonics and how the lithosphere is this outer shell and it's divided up into plates like a puzzle piece. And these plates are represented in different ways. Some of these plate boundaries pull apart from each other, and some of these plate boundaries collide. And when they collide, they can do three different things. For example, tectonic plates that are continental versus continental, they collide and they create mountains like the Himalayan mountains right here. And then we have, for example, we have plate boundaries and they pull apart from one another. And we have those examples. Those are called divergent plate boundaries. We have this example in what we call the Mid Atlantic Ridge. It is actively pulling apart, which is one of the reasons why where you can see South America used to fit very, very nicely into the continent of Africa. And they've just been pulled apart from one another. We also have this divergent plate boundary happening here in the Red Sea and what we call the Horn of the continent of Africa. This whole area has been pulled apart. Saudi Arabia has been pulled apart from the continent of Africa and actually created an ocean we call the Red Sea. This continues to happen here as this eastern horn of the continent of Africa is actively pulling away from the other part of the continent of Africa. We also have what we call a convergent plate boundary, where an oceanic plate collides with a continental plate and creates what we call subduction zones. And this is when you have an oceanic plate and a continental plate collide. And an oceanic plate dives underneath the continental plate. Oceanic plates are always going to subduct or go underneath a continental plate and that creates volcanoes in the example that we have in Cascadia up in Oregon. Now, this map that we're looking at here is going to represent the plate boundaries that we have across the earth. These dots are going to represent earthquakes or epicenters. Now, the difference between a focus and an epicenter is very important. A focus is the actual location where the earth has moved, where the earth has slipped. This occurs usually miles or kilometers below the earth's surface, where these plate boundaries really intersect and interact. The epicenter is the location on the Earth's surface. The epicenter is something that we as humans really relate to because we live on the surface of the Earth, right? We don't live 2 or 3 or even 20 miles below the Earth's surface, do we? So we want to know the location on the Earth's surface where the earthquake happened. So, what we're looking at in terms of red dots are the epicenters of earthquakes. What you'll notice is that these are largely based on where we're going to find plate boundaries. Here we have Southern California, we have the San Andreas Fault. It's a transform fault. Transform faults means they slip past one another. So we actively have part of Southern California is being displaced and moving away only at centimeters. So these movements actually occur over millions and millions and millions of years. You're also going to see a lot of earthquakes and volcanoes along what we call the Pacific Ring of Fire. Here we have Indonesia. This is Papua New Guinea. This is New Zealand down here. Here we have Indonesia. We have the Philippines. This plate here is actually called the Philippine Plate, and then we have Japan. What's happening here is we have an oceanic plate diving underneath a continental plate and creating volcanoes. Japan, very famous for its volcanoes. Indonesia, very famous for its volcanoes. And the Philippines, famous for typhoons, which are hurricanes, earthquakes, and volcanoes as well. Here is another very, very beautiful photo of vibration in the earth produced by shock waves due to sudden displacement of the earth's faults. So here you can see very beautifully this Pacific Ring of Fire, where you're looking at the earth and most notable shock waves where you'd be surprised that along the San Andreas Fault sometimes there are tiny, tiny little earthquakes that you and I just don't feel. As well, there are tiny, tiny little earthquakes represented up here along the Cascadia Fault zone in what we could consider Northern California, Oregon, and the state of Washington. Here you will see this travels up into Alaska, along the Aleutian Islands, and down into what we consider this is Russia, into Japan. And here's the Philippine Plate. Here's the Philippines. You've got Indonesia up in here into Thailand, around to Papua New Guinea, and down through New Zealand. This is also represented here all the way down the coast of Mexico through Middle America. Costa Rica has earthquakes and volcanoes, and all the way through Middle America around the Andes Mountains as well. The most notable fault that we have in Southern California is called the San Andreas Fault. The San Andreas Fault runs through the Imperial Valley, up in through Palm Desert, through Central California, and actually out through the city of San Francisco. So here is a better idea of this fault area in Southern California and the other associated faults that actually are responsible for the creation of so many mountains in Southern California. So we have the Santa Monica Fault that is responsible for, you've got the Santa Monica Mountains here, the San Gabriel Mountains here, and you've got the San Bernardino Mountains here. You've got the San Jacinto Fault. It's responsible for the San Ysidro Mountains. You've got the Elsinore Fault that is responsible for the Santa Ana Mountains. So we have lots of mountains in Southern California, all there because of faults. As we've said before, the San Andreas fault line is a strike slip or what we also call transform. What does that mean? That means that two faults, they're not pulling apart from each other and they're not moving towards each other. They're actually slipping past one another. Here you can see an actual aerial photo of if you would go to Wallace Creek in California. That is actually just in central California. I've actually tried to drive here before. It was pretty fun. And where you can see the water drainage patterns are actually offset from one another. And that's how you can tell that the San Andreas Fault is running right through here. Here is another example of the San Andreas Fault as well. It's pretty obvious when you see it from certain vantage points, isn't it? Here's an example in an urban environment of what happened in Hollister, California, because of the San Andreas strike slip or transform fault, where you had a piece of sidewalk that's displaced from another piece of sidewalk. And for example, most Southern Californians live on the Pacific Plate, whereas the rest of Americans live on the North American Plate. So let's say, for example, that you would like to drive to Vegas or you would like to drive really to anywhere else that's on the other side of the San Andreas fault line. So if you drive from LA to Las Vegas, if you drive from LA to Big Bear, if you drive from, let's say, LA to Apple Valley or Victorville, you're actually going from this, everything on this side is the Pacific Plate, and then everything on this side is called the North American Plate. So you're actually moving from one plate to the next. And this photo represents that very well. Here is the Pacific Plate, and here is the North American Plate, with most of the United States population living on the North American Plate. Here is an example, fence somewhere in California, where you can see that the two have been displaced somewhat. So, for example, here you go. Here's the Pacific Plate that's moving up and away in a north-northeasterly fashion, and here is the North American Plate. Wow, this is an older photo, shows you the results of earthquakes over time. So this fence was offset by 2.6 meters in a very, very large magnitude earthquake in 1906 in San Francisco, California. That's a very obvious and a very radical example. Here is an example of one of the larger earthquakes in 1979 in the Imperial Valley, which if you would go, if you drive, say, to Palm Springs and then to Indio, and then you keep driving south along the Salton Sea and continue driving south, that is the Imperial Valley. It's a big place for farming, huge for farming, but it also is the location of the San Andreas Fault. Here are a few more other examples of unfortunate earthquakes and the specific one that we were talking about right now. And maybe an earthquake that is more in the forefront of your memory is the earthquake that unfortunately caused the very large tsunami and a huge, huge loss of life in the northern part of Japan in Sendai province. This also was the result of a huge nuclear disaster as well in the Daiichi plant. So, what ended up happening is you have a fault boundary right here. The little teeth represent a convergent plate boundary, which means that this oceanic plate is diving underneath a continental plate. And what happens is you have movement. This movement or this movement of this plate creates an earthquake. And as you can see, the earth actually shifts. So this happens in the ocean as well. So the earth shifts in the ocean. And what happens is that millions and millions of gallons of water are displaced. And when they're displaced, they come rushing. And when they come into contact with continent, unfortunately, it's not a tidal wave, it's a wall. It's a wall of ocean that keeps coming. So the people in the Sendai province, they knew that this tsunami was coming because they have buoys, they have also have tsunami walls all throughout Tokyo, all throughout this side, especially of Japan. And so they all of their alarms went off and they knew that they had 20 minutes to get to a higher place. Unfortunately, they didn't realize how large that tsunami was going to be, and the results were catastrophic. As you can see, the epicenter of this earthquake was very, very near, extremely near to Japan, right off the coast of Japan. The reason for that, they have a plate boundary right off the coast of Japan. Here you can see the predicted tsunami wave heights in relative condition in the entire Pacific Ocean. So we did have a little bit here over on the west coast of the United States. Obviously, it took a few hours to get here, but unfortunately for the people here in Sendai province, that wasn't the case. Here is what happened. It's not only a tidal wave, it's the entire ocean that comes in and it doesn't stop. Here is unfortunately the plant. Here is the nuclear plant that was unfortunately released a lot of emissions. Here is a video on YouTube to go over and help you understand why sometimes earthquakes are so hard to predict. Many times they'll tell us, "Oh, we're in for a big one," or it's predicted we're going to have a big one, but we just don't know when they are going to happen. Is there risk involved in living in places where there are earthquakes? Absolutely, yes. But the nice thing is that in Southern California, we're very lucky to live in a location where we have engineers who are updating and designing our hospitals, our roads, our bridges, our freeways to be earthquake protective. For example, if you are driving on a flyover bridge on a freeway, you'll notice that every single panel, um, I think it's every 60 feet, has actually a buffer zone so that when we do have an earthquake, the concrete just won't break. It is actually given room a little bit to move. The same goes for our large hospitals. They're all built on rollers. The reason for this is that if there was an earthquake, they need to be able to have some sort of flexibility. Well, let's take a look at where the faults are in the United States. Well, by now we should have a good idea of where they are. Where are most of the mountains in the United States? On the western side, correct. Here we have most of our fault lines in the United States, the largest one obviously being the San Andreas Fault that goes right through Southern California. And it's obviously what Southern California is also very famous for. Here we also have a fault line that's just off the coast of this is Northern California, Oregon, and the state of Washington. This is also Canada, Vancouver Island, and you have a very small plate right here as well, which this plate right here is the reason for the Cascade Volcanic Mountain Range. So now it's time to reflect, review, and reflect. Think about 3 interesting things that you learned in this lecture. Think about 2 confusing things, and think about 1 burning question you might have. Think about it and share it, and then look into it a little bit further. What's most important about this is that you take notes on this because we're going to have labs and work that are associated with these lectures and learning about such things. So I encourage you to go ahead and go over these lectures a few times if you need to. And if you feel like you're just not getting it, that's what I'm here for. Contact me and let me know how I can continue to support you. I'll see you soon.